Most light aircraft use a direct current, or DC supply, to drive the electrical services. The term direct current implies that the electrons which make up the flow of current are travelling in one direction only. Convention states that the electrons flow from a positive source to a negative. Alternating current, on the other hand, has the electrons in the circuit moving backwards and forwards about a mean point. The number of electrons flowing past any one point in a conductor is measured in amperes, or amps for short, on an ammeter. Imagine the current of electrons flowing through a wire as being the same as water flowing in a pipeline. This is called the water analogy, and for people not too well acquainted with electricity, the water analogy can come in very handy in almost all situations when dealing with simple direct current circuits. So, as with any simple plumbing system, for the water to flow through the pipe requires that we have a pressure. This pressure is usually obtained from a water tank, which is placed above the level of the whole water system, and thus gravity helps us out. In an electrical circuit, the pressure required to move electrons along a wire is termed the electromotive force, or the voltage, which is measured in volts on a voltmeter. We can obtain this electromotive force, or voltage, from any of several sources. In a light aircraft, the main source of supply is the generator, or alternator, and the battery serves as a backup in case of alternator failure. The battery can run the aircraft's essential services for about 30 minutes. The battery also supplies power for engine starting. Resistance is the obstruction in a circuit which opposes current flow. Using the water analogy, you could imagine that a kink in a hosepipe would restrict the water flow. Likewise, a resistor placed in a circuit would lower the current flowing in that circuit. The supply is fed to the electrical components of the system via busbars, which are merely collection and distribution points. The busbars are usually solid copper bars which are drilled and tapped so that supply and distribution cables can be attached to them. Most light aircraft which utilize metal construction are single-pole or earth-return electrical systems. This means that the individual components are supplied via the busbars and cables, and to complete the circuit, the return current flows back through the metal of the airframe. Aircraft which are made of non-conductive materials require a double-pole or two-wire system. This means that as well as having a cable taking the current flow to each individual component, another cable is required to complete the electrical circuit back to the negative side of the generator or alternator. This is probably a good time to explain the use of the two terms alternator and generator. Simply put, a generator produces direct current, while an alternator produces alternating current internally, using a diode rectifier to turn the alternating current into direct current, which is then fed to the aircraft circuit. Alternators are used much more in all applications where a dependable power supply is required. Whereas a generator will probably require the engine to run at approximately half speed before it will deliver its full output, an alternator will give almost full power at engine idling speed. A battery is made up of a number of cells which convert chemical energy into electrical energy by a transfer of electrons from one material to another. There are two types of cell, the primary and the secondary. The primary cell is the type normally used in handheld equipment, like torches and transistor radios, etc. It consists of two electrodes immersed in a chemical called an electrolyte. The electrolyte encourages electron transfer between the electrodes until the electron imbalance between them exists as a potential difference, or voltage. A voltage of approximately 1.5 exists between the electrodes of a new primary cell. For convenience, One of the electrodes is used as the container for the electrolyte, and the other electrode is placed within it, as shown here. When the two electrodes, now called the positive and the negative, are connected to an external circuit, electrons flow through the circuit. This external transfer of electrons is matched by an internal transfer from the positive to the negative electrode. As this circulation of electrons continues, the negative electron slowly dissolves into the electrolyte until it is eventually eaten away. At this point, the cell is dead. Once discharged, primary cells cannot be recharged. Secondary cells work on the same principle as primary cells, but the chemical energy in the cell can be restored when the cell has been discharged by passing a charging current through the cell in the reverse direction to that of the discharge current. In this way, the secondary cell can be charged and discharged many times over a long period of time. During charging, electrical energy is converted into chemical energy, which is retained within the battery until it is once again discharged. The lead-acid battery is most commonly used in light aircraft. The electrodes in a lead-acid battery are called the plates. There is a positive plate, which is made of lead peroxide, and a negative plate, which is made of spongy lead. Both of the plates are immersed in an electrolyte of dilute sulfuric acid. The state of charge of a lead-acid cell can be determined by measuring the specific gravity of the electrolyte solution with a hydrometer. The electrolyte of a fully charged cell will have a specific gravity of approximately 1.3, whereas the electrolyte of a discharged cell will have a much more dilute acid, with a specific gravity somewhere in the region of 1.17. The voltage of a lead-acid battery cell when it's off-load or not passing current is 2.2 volts. Apply a load to the terminals of the cell and the output voltage will fall to just 2 volts. The capacity of a cell is a measure of how much current it can provide over a certain period of time. The capacity of a cell is determined by the area of the electrodes, or plates as they are called in a secondary cell. Capacity is measured in ampere hours. A cell with a capacity of 80 ampere hours should provide a current of 8 amperes for 10 hours, or alternatively 80 amperes for 1 hour. However, because the ability of a battery to retain its output voltage diminishes as the discharge rate increases, capacity is normally tested at the 10-hour rate. It's not normal to use cells in isolation in aircraft batteries. Usually they are placed in series or in parallel with others of the same voltage and capacity. This cutaway diagram shows 6 cells in series with each other. This circuit diagram shows cells connected in series. Notice how the voltage of the circuit increases as more cells are added. Note also, however, that the capacity of the system remains the same as the capacity of one cell. This diagram shows cells joined together in parallel. Now the output voltage of the circuit is that of just one cell, but notice that the total capacity is the sum of the individual cell capacities. To charge a battery, it must be connected to an electrical supply which has a slightly higher voltage than that of the battery itself. When the battery is being charged, great care must be taken regarding the rate of charge. If the rate of charge is too high, then gassing will take place. Gassing is the formation of hydrogen gas on the plates. The gas must be allowed time to escape through the vent cap of the battery. If too much gas is produced in too short a time, then there's a danger that a build-up of gas pressure could cause the battery to explode, with the subsequent release of the sulfuric acid within. Under normal circumstances, the output voltage of the alternator or generator charging a 12-volt battery on an aircraft would be maintained constant at 14 volts, whereas the alternator of an aircraft with a 24-volt system would be maintained constant at 28 volts.